As a chemist, you care about what your molecules actually look like. Well, at least you should. You want bond lengths, angles, dihedrals, and three-dimensional volumes that reflect reality, not just a sketch on a bar napkin. Structure dictates function. The pose and relative strain of a drug candidate, the flow of electrons in semiconductors, identification of a macrocycle with two-dimensional NMR spectroscopy. Basically, if your starting geometry is garbage, every property you calculate after that, structure, reactivity, spectra, is also garbage. You need to get this right. This is where geometry optimization comes in. And no, I don't mean being all that you can be in a 10th grade math class. Geometry optimization refers to a computational process to find the most stable arrangements of atoms in a molecule. The method works by adjusting positions of atoms over and over until there is no readily accessible lower energy state. It has profound implications in how we use computational chemistry to model the world around us. While one can get into the mathematical weeds rather quickly, practical implementation of this method is easy to learn, but difficult to master. Today, we'll look at a few tips for finding stable molecular structures, without losing your mind. And for the skeptics out there who think computers are just guessing, stick around. I'll show you where algorithms tend to fail, and why you should learn to embrace them in spite of their failure. So what is geometry optimization? Simply put, it's the process of finding the most comfortable position for a molecule. Software calculates the exact force pushing or pulling on every atom in a molecule. Then it uses those forces to nudge the atoms, step by step, until they settle into positions where they aren't being nudged anymore. One way to find this energy minimum is with molecular mechanics. This is the classical physics approach. Atoms are treated like balls connected by springs, applying Hooke's law to define the force on each atom as a function of bond length. Every bond oscillates tightly around an equilibrium distance in which the forces experienced by the atoms are essentially zero. If the atoms are pulled apart, restoring forces pull them back. If the atoms compress together, restoring forces push them out. The computer uses equations called force fields to model how much energy it takes to compress or stretch those springs. Geometry optimization methods are parametrized with different force constants to describe each bond. These force constants have been derived over the years with precise spectroscopy measurements. A double bond is a stiffer spring than a single bond. A triple bond? Even more so. Not only atomic bonds, but angles between 3 atoms and dihedral angles between 4 atoms are all collected and summed in an equation to describe the energy. Along with van der Waals and Coulombic interactions, these terms combine to model the conformation-dependent energy of a molecule. But let's be real. While molecular mechanics formalism treats bonds like nice, well-behaved springs, that's just a useful lie. Atoms aren't hard plastic spheres, and bonds aren't springs. Molecules contain dense nuclei surrounded by chaotic clouds of electrons. Molecular mechanics methods can't simulate chemical reactions. They weren't designed to describe bond breaking and forming. Molecular mechanics are incapable of handling non-classical effects like hyperconjugation and aromaticity. To model that level of reality, we have to transcend classical physics and bring in the heavy artillery. We need quantum mechanics. Schrödinger equation, wave functions, probability densities, and all that. These methods don't model atomic behavior based on spring constants. They calculate interactions of electrons in orbitals. These methods, while differing in formalism, are all applicable in their respective domains, but you can be sure to pay for this accuracy and time investment. Not all methods are created the same. There are semi-empirical methods, density functional theory methods, coupled cluster methods, and so on. We won't concern ourselves with that level of detail in this video. Let's talk about where the process of geometry optimization goes wrong, because it will go wrong. Pitfall number 1, we'll call garbage in, garbage out. Geometry optimization is an algorithm, a set of directions to get from one conformation to another. If your initial structure contains overlapped atoms or any other structural anomalies, your solution will be wrong. The computed forces will likely be so high that your simulation will explode. The more technical term would be divergence. So make sure you fix overlapping atoms and unphysical initial structures before you click run. Pitfall number 2 is believing that all methods agree. Here's an example using a potential drug candidate called rosatopopt. I generated 3D conformations of this molecule and calculated the energies using molecular mechanics, the spring-based method. Then I optimized the set with quantum mechanics, the wave function method. The ensemble energies mostly agreed, except for the most important part. Molecular mechanics predicted the wrong energy minimum.
Look at this graph.
If I had based future analysis on this conclusion, it would be wrong. I would recommend that you use the FAST method to generate a set of conformers and then refine your results with quantum mechanics. Now grab your tinfoil hats because we're going to chase a 2018 synthetic study down a computational rabbit hole. We have here two possible dihydroxyphenone structures, an R isomer and an S isomer. The experiment says the ratio is 97:3 in favor of R. So I ran the numbers. Like before, I used molecular mechanics to generate conformers and calculate the energies of each isomer. The R stereoisomer was predicted to be more stable. Then I followed it up with high-level quantum mechanics. The expensive, arguably more realistic quantum mechanical method predicted S was more stable. It predicted the wrong major product. Even after Boltzmann averaging an ensemble of these conformers, it still predicted S. So what happened? Is the method broken? Did physics take a day off?
Watch your profanity.
Quantum mechanical methods are still approximations and models of reality. All models are wrong, but some are useful. Incorrect conclusions from studies like the one I've shown here happen all the time. I believe, in this case, it's caused by the underlying assumption that the observed product is the most stable one. That would mean that the reported selectivity was the result of thermodynamic control. But what if a less stable product can be formed on a faster timescale? This would be an example of kinetic control. And it's more prevalent than you might think. It's why the graphite in your pencil won't spontaneously turn to diamond. Diamond is, of course, more stable in a thermodynamic sense. It's likely that forming the R stereoisomer, which is the observed product, is easier and faster in this case. It has a smaller free energy of activation. It's important to note that I didn't verify this theory, so you decide if it's sensible or not. For these quantum level calculations, I spent 23 days of CPU time to get the wrong answer. Molecular mechanics only took a few minutes, and it got the right answer. So you may ask, why not rely on the FAST method all the time? Because you shouldn't compromise for more accurate models of reality. Quantum mechanical models aren't perfect, but they're rigorous. Ultimately, you want confidence that you've obtained the best answer possible for the right reasons. Molecular mechanics can't model bond breaking or electronic excitations. It can't model transition states that involve bond breaking or predict kinetic control. We've seen that its mathematical formalism can't even be used to rank conformer energies properly. With quantum mechanics, there's an added level of validation. We can compute analytical frequencies. These frequencies help map the curvature of the free energy space. Now this is a little technical, but if that calculation doesn't return any imaginary frequencies, we can be certain that we're at a true minimum on the energy landscape. Geometry optimization is powerful, but it's not a tool that can be wielded without knowledge of its underlying assumptions and limitations. For predicting selectivity in reaction products in my own cases, I always consider both thermodynamics and kinetics, which utilizes geometry optimization on two disparate types of stationary points, energy minima and energy maxima. If you'd like to know more about the kinetics part, finding the elusive transition state structure, then leave a comment and let me know. For additional computational chemistry content, check out my playlist. Thanks for your support. See you next time.